Hey everyone, Mr. Fransky here. Today we're going to be talking about the white AP sheet. This is just some more Taylor series problems that also involve error. So once again, there are some problems you're going to be able to do and some you won't, depending on where you are. If you've done all of Chapter 9, you're going to be able to do all these problems. If you've only done 9.1 through 9.2, then the first problem especially is going to be challenging, but the second one you should be able to do just fine. So let's jump in here and just see what's going on. So first up, we have f of x is the natural log of 1 plus x cubed. Now, one of our building blocks that we had was the natural log of 1 plus x, and they actually give us the Maclaurin series for that. So Maclaurin, remember, centered at x equals 0. They tell us the Maclaurin series for ln of 1 plus x is x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4, blah, blah, blah. And that comes from the fact that 1 over 1 plus x, remember, was 1 minus x plus x squared minus x cubed, because that's geometric, right? This is the antiderivative of that one. So they give it to us. That's very nice of them. They also give us the common term. You'll notice AP does this a lot. They don't usually give sigma. They just kind of give the in general term at some point. So they want us to use this series to write the first four non-zero terms in the general term from the Maclaurin series for f. So if this is ln of 1 plus x, I can get here by just replacing all the x's with x cubed. So ln of 1 plus x cubed is going to be x cubed minus, not plus, so minus x cubed squared over 2 plus x cubed cubed over 3 minus x cubed to the fourth over 4. So this is really just a building block problem. Blah, blah, blah. So 1, 2, 3, 4. That'll work. So that looks like, if we simplify a little bit, make it prettier, x cubed minus, remember power to a power, you multiply, so x to the 6th over 2. Then it'll be plus x to the 9th over 3, and then minus x to the 12th over 4. And there is our first four terms. Do they want the general term? They do. Okay, so the general term, if we do it the way that they did, you could also do it with a sigma, but basically it's still alternating, so we still have negative 1 to the n plus 1. So this must be, there must be starting at 1 with n, the way that they did it, but if you did a sigma, you could start it at 0, that'd be just fine. And then it looks like we just replace x with x cubed. So x cubed to the n divided by n. That's a cube, I promise. Okay, so there we go. So there's our first four terms and our general term. All right, moving right along. So now they tell us the radius of convergence from the Maclaurin series is 1. This is something we haven't talked a lot about until 9.4. So if you've done 9.4, you should at least be able to kind of get an idea of what's going on here, but 9.5 is really what's going to solidify this. So they tell us that radius of convergence from the Maclaurin series is 1. Radius always is absolute x minus a is less than capital R. That's your radius of convergence. So in this case, a is 0, right, because we're centered at 0. So that tells us that absolute x minus 0, I'm not going to write that, has to be less than 1. So they're telling us that's the radius of convergence. Now that kind of makes sense, because this guy came from the building block of 1 over 1 plus x, so we know that this converges for absolute x less than 1. So this must also converge at absolute x less than 1. So then it kind of makes sense to me that the 1 plus x cubed, just replacing the x with x cubed, should also converge for absolute x less than 1. Now they want to know the interval of convergence. So in 9.4, what we learned is the ratio test tells us the radius of convergence. But then we have to figure out, there are three options. It's either negative 1 less than x less than 1. It could be negative 1 less than or equal to x less than 1. Negative 1 less than x less than or equal to 1. I guess there's 4. Negative 1 less than or equal to x less than or equal to 1. The question is what's happening at the endpoints. So I don't know which one of these it's going to be. I think this is kind of one of the textbook ones, so let's just see what happens at those endpoints. So the way we do this is we know everything between negative 1 and 1 is good, right? That's for sure good. The question is, do the endpoints work? So we plug them both in and we see what happens. So let's go back to our series here. So if I plug in, let's do positive 1 first. So if I plug in positive 1 here, let's see what we get. We would get 1 minus 1/2 plus 1/3 minus 1/4, etc., right? So it'd be negative 1 to the n times 1 over n. This is the alternating harmonic series. This is one that we will see a lot if you haven't seen it already. The alternating harmonic series converges, and that's well known. Alternating harmonic series converges. I would write something like that. Okay, this is by the alternating series test. And the reason that works is because we have an alternating series, right? That's clear. And the terms are getting smaller. So we do truly alternate. They are getting smaller all the way to infinity, and that's really all you have to check for alternating series test. Okay, so when we have positive 1, we know it's going to be good, okay? So it's not going to be either of the first two, because those have positive 1 not working. So now we have to check negative 1. So positive 1 worked out, right? So notice there are no x's left. We actually are just checking the series here using a number. Let's try negative 1. Okay, so if we do negative 1, the first term will be negative 1 to the third power, which is negative 1. Okay, so we'd have negative 1. And then the next term, negative 1 to the sixth, is positive 1 over 2, so we'd have negative 1/2. The next one, I think, is an odd power, so we have negative 1 to the ninth is negative 1 over 3 is negative 1/3, so minus 1/3, and then minus 1/4, etc., etc. So this time we're subtracting all. So you could pull a negative to the front, and you'd have 1 plus 1/2 plus 1/3 plus 1/4, etc., etc. And this is the harmonic series which diverges. And that's well known as well. If you need a reason, it's by the integral test. And that's because the integral of 1 over x diverges. But you can just say harmonic series diverges. That's all you need. So it's not good at negative 1. So that means that our interval of convergence is negative 1 less than x less than or equal to 1. That is where it is going to converge. Okay, because it doesn't work at negative 1. So this you probably weren't able to do because I probably gave the white sheet a little bit too early. But that's just fine. So let's move on. The next part we should be able to do. Part D we won't be able to do though. So now they want the first 4 non-zero terms of the Maclaurin series for the derivative of t squared. Okay, well, we know that f of x was x cubed minus x to the, I gotta check, I think a sixth, right? Is it every 3? Yep, so minus x to the sixth over 2, and then it was plus x to the ninth over 3, and then minus x to the 12th over 4. This pattern keeps going. So then f prime of x would be 3x squared minus 6x to the 5th over 2 plus 9x to the 8th over 3 minus 12x to the 11th over 4. And if you're out there saying, why aren't you using quotient rule? Because these are constants on the bottom, right? We can just pull them out, do the derivative of the x, bring it back in. But I don't bother with that, right? Okay, so that keeps going. And they want it to be f prime of t squared. So f prime of t squared then would be 3t to the 4th. I'm going to just do these powers in my head. Minus 6t to the 10th over 2 plus 9t to the 16th over 3. Goodness gracious. Minus 12t to the 22 over 4. And we keep going. Okay. Now they tell us g of x is the antiderivative from 0 to x of f prime of t squared. Okay, so g of x is going to be the integral from 0 to x of 3t to the 4th minus 6t to the 10 over 2, 9t to the 16 over 3. I'm just going to do that because they only want us to use 2 terms. Okay, so that's going to be, let's see, 3t to the 5th over 5 minus 6t to the 11 over 22. And that's going to keep going. Man, those are fun numbers. Okay, they want us to use that to approximate g of 1, just the first 2 terms. So g of 1, thank goodness it's 1, is going to be 3/5 minus 6/22. We can reduce that to 3/11. Wow, okay, so you could circle that and be done, but because I am a glutton for punishment, we're going to find a common denominator here. So multiply by 11, that's 33 minus 15 over 55. Right, because 11 times 3 is 33, 5 times 3 is 15, yep. So 33 minus 15 is 18 over 55. There you go. Okay. Well, that was fun. Now the last one they're going to ask us about error, I'm pretty sure. So the Maclaurin series for g evaluated at x equals 1 is a convergent alternating series with individual terms that decrease to an absolute value to 0. Those are all of the conditions that you need to use the alternating series test. So they give them to you. So that your approximation to part C must differ from g of 1 by less than 1/5. So remember, alternating series test just tells us that the next term is going to be the error bound. So if I go one more term here, let's see, it would be 9t to the 17th power divided by 17 times 3, which is 51. Nice. Okay, so if you plug 1 into that, so we're using 9t to the 17 over 51. 9t to the 17th power, that's t down there, over 51. We're going to evaluate that at t equals 1. Okay, so we plug 1 in there, we get 9 over 51. So the question is that less than 1/5? Well, 10 out of 50 would be 1/5. Let's see. 9 out of 45 is 1/5. So let's see. So this is equal to 9 out of 45. That's probably the easiest way to think about it. So 9 out of 51 is indeed less than 9 out of 45 because the denominator is bigger. So that checks out. Okay. Now, I realized one mistake I made here. I should have changed these to x's, right? So at this point, what I should have done is done the antiderivative. So minus blah, blah, blah. Plugged in 0 and x. But notice once again, like usually happens with these, when you plug in 0, everything's going to go away. So I really should have rewritten this with x's, with all the x's dumped in, and then the zeros just disappear. Okay. So really these should be x's. It should be 9x to the 17th. Evaluate that at x equals 1. And then that gives us the 9/51, which indeed is less than 9/45 or 1/5. Okay, that's one problem down. One to go. Sine x squared plus cosine x. Looks like we're going to be using building blocks here. And the graph of the fifth derivative is shown above. I don't have that on this page because it's not going to be important for this part of the problem. So first they want us to write the first 4 non-zero terms of the Taylor series. So first let's remember what Taylor series is, right? And they want it centered at x equals 0, so it's going to be f of 0 plus f prime of 0 plus f double prime. Oh, I'm doing this way harder than it has to be. But this is the beginning of the Taylor series. I should have an x on the one, but that's okay. So they just want it for sine. Sine is one we have memorized, right? So sine, they want the first 4 non-zero terms. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. 1, 2, 3, 4 non-zero terms, okay? Then they want the first 4 non-zero terms for the Taylor series for x, sine of x squared. So, did they want general terms? Nope, they don't. So sine of x squared, I'm just going to replace all the x's with x squared. So I have x squared minus x squared cubed is x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial. Okay, there we go. So that was part A. Now for part B, they want the first 4 non-zero terms of cosine. So cosine is the evens. Man, just racking up free points here, right? 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, etc., just all the evens. Don't want the general, okay? So then use this series and series for sine x squared from the last one, right? The first 4 non-zero terms of f. Okay, so f of x is sine of x squared plus cosine x. Now let's think about our constant term, right? So if we look at these two series right here, we're going to try to increase this by order of power. Okay, so our constant term is going to be 1, right? So we see that right here. Now next we have a couple x squared. So what I'm going to do is I'm going to pull the x squared out and do the constants, right? So we have 1 x squared here, and we have a negative 1/2 x squared here. So I'm going to write 1 minus 1/2 x squared. Now the next term, looks like we have a 1 over 4 factorial. So I'm going to think about that as 24, right? 4 times 3 times 2 times 1 is 24. So I'm going to have a 1/24. So look at it. Oh, nope. Lies. There's only one x to the 4th term. The next one's x to the 6th. So the next one is going to be just 1 over 4 factorial. X to the 4th. That's the only x to the 4th term. Jumped ahead of myself with the 6. Okay, so the next one, now for the x to the 6th term, I have 2. Right, so we use the x squared terms. Got our x to the 4th term was alone. X to the 6th, we have these 2. So I'm going to have a negative 1 over 3 factorial, which is 1/6. Minus, looks like 1 over 6 factorial. 6 factorial is 720. Goodness, 1 over 720. You could write 6 factorial, that's just fine. And that's x to the 6th. Okay, so that is the first 4 non-zero terms. You could circle it and be done. I might make it pretty, just in case you did as well, so I want to make sure that we got the same answer. So that would be 1. 1 minus 1/2 is just 1/2, so I'd have x squared over 2. Next up, we got x to the 4th over 24. And then we have negative 6 minus 1 over 720. So this is 6 times 120. So I would have plus a, let's see here, let's just do a subtraction because it's going to be a negative number. So this is, we said 120 over 720. So it's going to be negative 121 because we have a negative 120 minus 1 more over 720 x to the 6th. All right, so there's our first 4 terms. Lovely. Now they want to talk to us about error. So find the value of the sixth derivative of 0. Now, this is a very important problem because the AP asks about this kind of stuff a lot. And so here it's really important to remember the terms of a Taylor polynomial, f of 0 plus f prime of 0x plus f double prime of 0x squared over 2 factorial. And that's going to keep going. I'm going to jump to the sixth one. So it's going to be the sixth derivative of 0, x to the sixth over 6 factorial. Now, what is happening here is that I think the most concrete way to think about this is the powers of x, whatever coefficient is in front of them, is going to have to do with that number. Okay? So, in this case, I'm looking for f6 of 0. Well, I know that f6 of 0 times x to the sixth over 6 factorial is going to have to be equal to whatever it is in my series. So in my series, what do I have in front of x to the sixth? I have 121 over 720, and it's negative. So this has got to be equal to negative 121 over 720, which is 6 factorial, x to the sixth. Okay, so these two things have to be the same. So if I multiply both sides by 6 factorial, those cancel. And this always works. Anytime they ask for a certain derivative, just set it equal to the term that has the same power of x, because I want those to cancel. So it looks like the sixth derivative of 0 is negative 21. Gosh, I hope that was right. There we go. Okay. So now they say let P4 be the fourth degree Taylor polynomial for f about x equals 0. So they're stopping here. Okay. So 1, I think I can remember that. 1 plus x squared over 2 plus x to the fourth over 24. Now the bummer about this is it's not alternating, right? So we're going to have to use Lagrange. So what they say is there's something about the next derivative, which thank goodness is the fifth. So there's something about the fifth derivative of some value c times x to the fifth over 5 factorial, where c is between, in this case, 0 and x. There's something between 0 and x that makes this the perfect error. I'm more concerned about the bound, right? So they want to show me here that the error, right, the absolute value here, p of 1/4 minus f of 1/4, that's the difference between the polynomial approximation and the actual function value. They want to show it's less than 3,000. Okay, well, if I know c is between 0 and x, so x they want me to use is 1/4 right here. So c is something between 0 and 1/4. Let's see what's going on in the graph. So here's 0, this is 1, so this must be 1/4. So between 0 and 1/4, what do we know about the derivative? What does it not go above? Well, if we look at this, I mean, here, this is the maximum value it attains. I don't really know exactly what that is, but it for sure doesn't go above 40, right? So maybe we use 40 for that bound. If we say, well, we know it's not bigger than 40. Let's see if that's going to get us under what we need to be. So if I do 40, x is 1/4, so 1/4 to the fifth over 5 factorial. Okay, well, 4 to the fifth. If you don't know that off the top of your head, right, this is a no calculator problem, what you could do is you could say, well, I have 40 times 1/4 to the fifth, because 4 to the fifth is a pretty big number. 4 goes into 40 one time, right? So I could think about that as 10 times 1/4 to the fourth. So that might make your calculations a little bit easier. Maybe not, but maybe. Okay, so let's see here. So then this is the same as 10 over 4 to the fourth times 5 factorial. Got big numbers here. So we can cancel some stuff out though, right? So let's see, 10 over 5 factorial. There's a 5 and a 2 in there. So that'll cancel out with the 10, right? So let's rewrite it. Let's think about it this way. So we have 10 over 4 to the fourth times 5 times 4 times 3 times 2 times 1 technically, right? Oh, go back. Get back to where we were here. Come on. Sorry. PowerPoint's still freaking out a little bit. Okay. So the 10 cancels with the 5 and the 2. Oh, we have red now. What a deal. So this is 1 over 4 to the fourth times 4 times 3. So 4 to the fourth, we weren't able to avoid this. So 4 to the fourth, 4 cubed is 64 times 4 is 256. So we have 1 over 256 times 4 times 3. Oh, why do you keep doing this? Wow. Sorry, guys. We're almost done, too. So 256 times 4 is 1024. Times 3 is 3072. Goodness, this is 1 over 3072 which is indeed less than 1 over 3,000. Thank goodness. Yay, put an exclamation there. It's not factorial, but I'm glad it's over. Okay, so we show that the error must be less than 1 over 3,000 by using Lagrange. So again, it was key that the derivative is always under 40. That was really what nailed this home. All right, that's the end of that one. I love you guys. That's why I'm here. Have a great day.